Okay, guys, this is our last chapter for the first semester. Last chapter. But it is the most important one. We need to pay very, very close attention. This is the most challenging chapter for AP students in the year. The objectives: we will be able to list the general properties that characterize acidic and basic solutions and identify the ions responsible for these properties. We will define the terms Bronsted-Lowry acid and base and conjugate acid base pair. We will define an acid or base in terms of the Lewis concept. Okay, your homework is Quest Acid Base Chemistry 01. We may have 02, 03, 04, and even 05. So this is the first one for chapter 16. Properties of acids. You learned this from first year chemistry. Remember, acids, they taste sour. Bases taste bitter. Bitter. Acids, what? Change the color of indicator. Bases, they feel slippery. Acids are corrosive. Bases are corrosive. Just review the different properties of acid and bases. You need to know 3 different definitions of acid and bases. 3 different definitions. Here's the first one. The Arrhenius is the more narrow definition. It is more limited. Arrhenius says an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ion. It is, like I said, it is more limited than the other 2 definitions. It said that acid has to have hydrogen and it has to be in water solution to increase the ion concentration. Base. Arrhenius definition of a base: substance that, when dissolved in water, increases the concentration of hydroxide ion. According to Arrhenius, the base need to have a hydroxide in it. The second definition is the Bronsted-Lowry definition of an acid and a base. This is not one person, it is 2 guys who came up with wrote the same paper at the same time. So they give credit to both of them, Bronsted and Lowry. According to Bronsted and Lowry, an acid is just a proton donor. Does not say anything about dissolving water, doesn't have anything to do with it. Is less limited. And according to Bronsted-Lowry, a base is a proton acceptor. Let me show you, when we talk about a proton in the chapter, we really mean a hydrogen ion, because as you know from the periodic table, hydrogen has 1 proton and it depends on the isotope, it has 1 proton. But if you, and then 1 electron. So if we have an H plus, we don't have that electron. The only thing you really have left is a proton. So when we said a proton donor, it really means a hydrogen ion donor. The same thing. So we will be using those 2 terms. We will interchange them. Proton and hydrogen ion. Third definition for acid is the Lewis acid definition. It is more broad than Arrhenius and Bronsted. If you remember from first year of chemistry, Lewis structure has to do with electrons, a pair of electrons. Acid, according to Lewis, is an electron pair acceptor. Remember, acid start with an A, acceptor start with an A. Lewis has to do with Lewis structures, which is electrons, pair of electrons. So it doesn't say anything here about having a hydrogen, doesn't say anything about being in water solution. It is broad. According to Lewis, a base is an electron pair donor. Electron pair donor. Let me give you an example. A famous weak base is ammonia. Okay, see, I write that ammonia is NH3. Ammonia does not have hydroxide. It's still a base. Okay, so if we draw the Lewis structure for ammonia, you have this is an H, this is an H, this is H, and there is a pair of electrons here. Okay, so if I have a hydrogen ion, this is our hydrogen. Okay. See if that ammonia give a pair of electrons to that hydrogen. Hydrogen will have those two electrons also. They are sharing that pair. That's why ammonia is a Lewis base. It is an electron pair donor. Okay, this is called a coordinate covalent bond. Okay, it is a covalent bond because they are sharing. It is called coordinate because that pair of electron is coming from only one of the elements. It's not that each one of them is contributing to that pair of shared electrons. Coordinate covalent bond, that the shared electron is coming only from one species. So this is a Lewis base. Now, another part we need to review from last year is conjugate acid base. Conjugate acid base. An acid and a base that differ only by the presence or absence of a proton. That means a hydrogen ion. Let's practice this. In the following reaction, identify the acid on the left and its conjugate base on the right. And identify the base on the left and its conjugate acid on the right. This is very, very easy and students get confused. Let me show you how easy it is. This is HBr. Its partner is Br minus. The only difference between those two is the hydrogen ion. The HBr has one hydrogen, one more hydrogen than Br minus. Therefore, this is the acid and this is its conjugate base. The only difference between an acid and its conjugate base is a hydrogen ion. That's all. I'm comparing those two partners. Don't write down partners on your AP test, please. They are not partners. This is me using a kid language to explain it. Okay, this is ammonia. This is ammonium. The only difference between those two species is a hydrogen ion. The ammonium has the extra hydrogen, so we call it the acid. The ammonia is missing that hydrogen. This is its conjugate base. What is the conjugate base of H2S? Let me reset this. The conjugate base of H2S, they're talking about conjugate base. All you have to do is take a hydrogen ion off. So it is H. This is S minus. Because I take a positive charge, H plus, become negative. H S minus is the conjugate base missing one hydrogen. What is the conjugate acid of NH3 minus? I just add a hydrogen and this is the conjugate acid. Conjugate, the only difference is a hydrogen ion. Now, acid and base strength. You learned from last year, the acid is, the strength has nothing to do with concentration. The strength has to do with degree of dissociation. Okay? If the acid dissociates completely in water, we call it a strong acid. A strong acid will dissociate completely in water. A weak acid only dissociates partially in water. So it has nothing to do with, like we said, with concentration. It has to do with degree of dissociation. Water. You learn from first year chemistry that water is molecular compound. It does not dissociate, does not conduct electricity. It was almost a truth, but we are going to show you a little bit of lie in it. Okay? Water is amphoteric or water is amphiprotic. I need for you to remember those two terms. Amphoteric, amphiprotic, they mean the exact same thing. That means Water can behave as an acid. Water can also behave as a base. And water is not the only one. Okay? It is not the only one. Amphoteric, amphoteric. So you have the water here, react with water. If this water is giving a hydrogen ion, it will become hydroxide. And this one, accepting the hydrogen ion, it is a hydronium. Remember, hydronium and hydroxide. In other words, water is behaving as an acid. Water is behaving as a base. And then I need for you to look at this arrow. It is equilibrium. Does not go to completion. This is an equilibrium. The ion product constant is, when you write down the K. The K, remember from chapter 16, it is, or 17, it is the product of the products over the products of the reactants. And for pure substance, pure solvent, pure liquid, pure solid, we do not use it. Therefore, you do not put it over the water liquid. That K for water has a special name. It is KW. Go figure. W for water. Okay? It is K at 25 degrees Celsius. Room temperature. KW equal 1 times 10 to the negative 14. And this is extremely important. We will be using this number throughout chapter 16 like crazy. And we will be using it not only for water, for any dilute solution. We will say KW equal 1 times 10 to the negative 14. So you need to know this very well. And remember, it is at room temperature. It is 25 degrees Celsius. So far you have learned so many K's. You have KEQ, you have KC, you have KP, you have KSP. Now you have KW. And guess what? If I don't have time today, in part 2, you will learn 2 more K's. Okay, now here's a practice problem. Why don't you get your calculator, please? We will do a quick math. Maybe you can do it in your head. I don't know. At 60 degrees Celsius, okay, not 25, 60 degrees Celsius, the value of KW changes. Okay, so it is not 1 times 10 to the negative 14. It is 1 times 10 to the negative 13. Using Le Chatelier's principle, here we go again. Predict whether the reaction below is exothermic or endothermic. Justify your answer. Okay, so is it endo or exo? I heard endo. Let's see how we can explain this. If I increase the temperature, my KW increases because 1 times 10 to the negative 13 is greater than 1 times 10 to the negative 14. So if I have heat right here, let's say if I put heat right here for exo, okay, I increase the temperature and it would shift the equation to the left, that making my KW less. So you are right, it is endo. It is endo. Because if heat is on this side and then I increase heat, it will shift the equilibrium to the right, making my KW greater than 10 to the negative 14. Therefore, it is endothermic. Now, calculate H plus and OH minus in a neutral solution at 60 degrees Celsius. So I need to use my formula KW equal the concentration of hydrogen ion times the concentration of hydroxide ion equal, in this case, 1 times 10 to the negative 13 because it is not at 25 degrees Celsius. So, because it is a neutral solution, concentration of H plus equal concentration of OH minus. Because it is neutral. Get the calculator ready for me, please. So, equal KW, it would be the square. That means it is the square root of 1 times 10 to the negative 13, which is, thank you, 3.16 times 10 to the negative 7. Is that right? Okay, alright. I'm checking 2 minutes before 55 because the bell rings at 55. So let me know when we have 2 minutes left. I will have no choice to stop. Ion product constant. Ion product constant. This is your KW. Your KW is called the ion product constant. So you can get your calculator. We can do this quickly. Calculate either the H plus or OH minus from the information given for each of the following solutions at 25 degrees Celsius. Okay, it is 25. And state whether the solution is neutral, acidic, or basic. Alright, if they give me OH minus, I can find H plus, concentration of H plus, calculator, equal 1 times 10 to the negative 14 divided by my H plus, my OH minus, which is 1.0 times 10 to the negative 5. Therefore, H plus concentration equal 1 times 10 to the negative 9. Now, let me ask you, which one is greater? The concentration of hydrogen or the concentration of hydroxide? Hydroxide is greater, therefore the solution is basic. It is basic. So, let's do this one. They gave me OH minus, I find bracket H plus. Okay, equal 1 times 10 to the negative 14 divided by 1.0 times 10 to the negative 7. Therefore, H plus equal, it is 1 times 10 to the negative 7, and the solution is neutral. Same number, same concentration of hydrogen and hydroxide, it is neutral. Now, wow, 10 molar. 10 molar, this is H plus. So concentration of OH minus equal 1 times 10, 1.0 times 10 to the negative 14 divided by concentration of H plus, which is 10.0. What is that? 1 times 10 to the negative 15 molar. Okay, and this is my OH minus. Therefore, the solution is acidic because my OH minus is way less than my H plus. Okay, you need to review your strong acids and strong bases. Strong acids and strong bases. Alright, let me quickly show you the strong acids, strong bases, and I will have to stop because the time is up. If you remember last year, your strong acids, go to group 17. HF is not a strong acid. HF is not. My strong acids are HCl, HBr, HI, HNO3, H2SO4, sulfuric acid, nitric acid, HClO3. Go to that Cl, make 2 more with that Cl. It is HClO3, O3, which is chloric acid, and HClO4, which is even stronger. HClO4 per chloric acid. You are responsible to know your strong acids. Any other acid that is not strong is weak. So those are 7 strong acids. What are the strong bases? The strong bases is the hydroxide of group 1, hydroxide of the metals of group 1, and the heavy metals of group 2. Calcium is at the borderline. Some books will note it, put it as strong, other books weak. It is at the borderline. So you need to know your strong acids, you need to know your strong bases. I guess I will have to stop right here because of the time, and I will do a part 2 starting with pH next time. Alright, so have a good rest of your day, and I will see you next class.